we know the expression, again, this is a known problem. Our differential equation looks something like RC dVc dt for voltage across the capacitor plus VC equals V source. And neglecting the right side, capacitor voltage. If we looked at resistor voltage, we know it takes the same form, dVR by dt plus VR plus some to be determined by the circuit analysis, but the left side's the same. So we went through all this, so I don't remember what it is off the top of my head, but we know these expressions. And again, we could look at current and the same story, RC dic dt plus IC equals something. And again, we derived it in the last class, so I just don't remember which one has a derivative, which one doesn't. But the left side is all the same. The differential side is all the same. And when we break up these solutions, we know our solution form, and again, it doesn't matter if we're talking about voltage across the capacitor, voltage across the resistor, current, whatever the case may be, but we can just write V of t equals some A1 e to the minus t over tau, and I'll write out tau for the moment, but we know what tau is, plus some forcing term. And we'll write it as a function of t. Here's our homogeneous solution. Component. And here's our particular solution component. And we know this depends on the source form. Whereas this exponentially decaying term just comes out of the differential equation. It satisfies the homogeneous differential equation, which is when all these guys are zero. So this is always part of every term. This depends on the source form, and we saw that in last class. And just to use a little bit of notation here, tau is called the time constant. And I left it a little bit general, but for the RC circuit, tau equals RC. And that's what we wrote in last class. We wrote minus t over RC. You'll frequently see tau. It means time constant, so just in case you haven't seen that before, make sure we introduce that to you. And we'll look at the RL time constant as well when we look at that term. So, every solution form for the first order takes a homogeneous and a particular solution. And as I said at the end of last class, this guy, largely for a general source, you need to get the particular solution from the differential equation. And we saw that quickly near the end of the class. Now, what we did take advantage of when we were looking at the steady state, DC steady state functions, which only corresponds to the step function by itself, then we can use the DC steady state. This winds up being a constant, and it's the DC steady state term. So our simplest function, our simplest source in some sense, and one we do look at quite a bit. Our step function source where the S of t equals some V naught U of t. And again, that looks something like V naught. And that's the source of t. And t, of course. So that's our step function. Well, our step function source the particular solution, the particular time equals a constant because that's the same form as the source. The source is a constant for t greater than 0. Again, all our solutions are for t greater than 0. And so our form takes a constant, which in this case corresponds to the DC steady state. And so you can get that directly from the circuit analysis. That's one of the advantages of the step function, its relative simplicity in terms of analysis. And we did all that in the last class. But just to remind ourselves again, this is a big review problem. We've done this quite a bit, but it's been a whole weekend, and I'm sure you didn't forget anything, but just in case. In this case, we can say the source of time. Let's say 10 minus 5 u of t. So there's an initial condition. As I look at this, though, what's the DC steady state value? What is the DC steady state value? As t goes to infinity, what's the voltage across the capacitor? 5. So for some value, as t goes to infinity, the source goes to 5, of course. And as t goes to infinity, we reach DC steady state. In steady state, we open circuit the capacitor. No currents flowing across that resistor, no voltage across that resistor then. We still apply KVL. We get the voltage across the capacitor as 5 volts. But regardless, we can take advantage. For the step function source, we know dc of t equals some form a e to the minus t over tau, which is 0.01. You get that from 100. Write this backwards, of course. 10 to the minus 4 gives us 0.01 plus a2. And so, well, in general, dc as t goes to infinity, we recognize that's a2. This term vanishes. Or if you want, we can write 0 plus a2. So as time goes to infinity, that exponential argument becomes increasingly large, and it's a negative exponential, so the exponential itself becomes vanishingly small. We wind up with 0 plus a2, which equals the DC steady state of the circuit. Always. In this case, it's 5 volts. We just did it by inspection, but that was 5 volts for our above source. And we know our initial conditions is 10 volts, so we can say VC of 0 minus equals VC 0 plus, and I'm sure we did this problem last week, so I'm doing it fairly quickly. But 10 volts for all time, or since the beginning of time, I should say. 10 volts since the beginning of time, so at t equals 0 minus, it's 10 volts. It's been that way since the beginning of time, which means we have 10 volts across the capacitor. And so that's 10 equals A1 plus 5, giving us A1 equals 5. And VC of t equals 5 e to the minus t over 0.01 plus 5. And we did that fairly quickly again, but using all the tools we saw last week. And again, I think we did this problem last week. Was there any questions on what I did here? That was fast. So if anyone's not sure, please say something. Now, how we started this discussion, we can get this term directly from the differential equation. We race through that at the end, but just to remind ourselves, our differential equation looks something like RC dVc by dt plus dc equals 5 for t greater than 0. Our source is known and it's a constant. T greater than 0 differential equation. Right? Source is known and it's a constant. Well, again, nothing's changed. VC particular is a constant. And we used just C naught last class. And if we plug that in, well, RC dVC particular by dt plus dC particular equals 5. Plugging in a constant, RC d by dt of C naught plus C naught equals 5. I hope we all agree that goes to 0, giving us C naught equals 5. We now know the particular solution, and this is an alternative approach. We could say VC in general now is VC homogeneous plus 5. And we know the homogeneous form for this differential equation looks something like an A1 e to the minus t over 0.01 plus 5. So we've gotten here the same way, from the DC steady state analysis or from the differential equation. And I will let you pick the one that you prefer. I don't care. I know a lot of you go home and solve differential equations, so maybe that's more attractive, whatever the case may be. How do we find our A1? We go back to the initial condition. V01 equals V0 minus equals V0 plus that we just did on the previous page. And we find A1 equals 5 for this particular problem. Now what happens when we do get a more complex source? For example, the source of t equals 5e to the minus 50t, u of t. So this is an exponential source that turns on at t equals 0. And if we want, we can draw it out. The source of t looks something like this. What are our initial conditions in this case? What are our initial conditions in this case? What does our t less than 0 circuit look like? Initial conditions are 0. Our t less than 0 circuit. No source. Oops, we got the resistor. No source is on. DC 0 minus equals 0. So we still have 0 initial conditions. If there's no source for t before 0, 0 initial conditions apply. It doesn't matter what source happens at t equals 0. And that's what this tells us. Nothing exists for t less than 0. So we have 0 initial conditions. IC for initial conditions. Well, what do we do now? We know the solution takes the form dc of t, still has an A1 e to the minus t over tau, where tau is RC. That's the homogeneous contribution now, plus the particular solution. What does our particular solution look like? It has the same form as the source. It has to. We don't know the coefficient, but we know the exponential argument. We know this term is an exponential. So we have plus A2 e to the minus 50t. Here's our VC particular. There's our VC homogeneous. And we could actually put some numbers in for tau, just so we can realize how great this problem looks. If I do a little inversion, we get minus 100t plus A2 e to the minus 50t. Well, once again, we have two unknown coefficients. How do we find A2? Then we absolutely have to go to the differential equation. There is no DC steady state analysis here because there's no DC term. For the particular solution. So we don't have a choice now. We can only use this kind of DC steady state shortcut for step functions. And again, that's largely what we'll look at, but it's important to be able to see this and recognize it. And so what do we do? Well, once again, 0.01, just to plug in some numbers, d by dt, where there's our particular solution, A2 e to the minus 50t plus A2 e to the minus 50t equals 5 e to the minus 50t. I didn't rewrite the differential equation, but does everybody agree with what I just wrote down? I substituted our particular solution into that differential equation. It was on the previous slide. Here's our source for t greater than 0, which was the right side. And then our RC term right there. So, one equation, one unknown now. We can multiply things out. Minus 0.05, not 0.5. Multiply it out correctly. A2 e to the minus 50t plus A2 e to the minus 50t equals 5 e to the minus 50t. I hope we agree that e to the minus 52 is the same everywhere. So we can cross that off by dividing through by e to the minus 50t. And what are we left with? A2 minus 0.5 plus 1 equals 5, giving us A2 equals 10. Right? And so, well, where are we now? Well, there's our half our solution, at least in terms of coefficients. We know VC of t now equals A1 e to the minus 100t plus A2, oops, let's write out 10, e to the minus 50t. Again, that's the particular and the homogeneous. And I just got that 100 just again to point out. 100 is 1 over 0.01, which was our time constant. Just wrote it out a little bit differently. And so how do we get the final answer? Well, VC 0 minus equals VC 0 plus, which was 0. And that winds up being A1 plus 10, implying A1 equals minus 10. And there's our full solution. VC of t equals minus 10 e to the minus 100t plus 10 e to the minus 50t. And that looks something, some gross exaggeration, that looks like that. So it satisfies our initial condition and becomes vanishingly small as t goes to infinity, which is what we would expect. We have that exponentially decaying source. Eventually that becomes vanishingly small and we're left with just an RC circuit with no source, so the voltage on the capacitor also has to go to 0. And that's it. So that's where all this comes from. You can always go back on a particular solution. And we'll set up one more just for fun. We won't finish it. Anybody still writing when moving stuff too fast? So on the same token, we can look at a sinusoidal source. And this is actually a real concern. So the source equals 5 cosine 50t u of t. And again, 10 to the minus 4, 100, so tau equals 0.01. Why is this a concern? I think I've mentioned it before, but this is a sinusoid that turns on at t equals 0. Where is this a concern? Where is this a concern? Yeah. Plugging something in. So in power systems, this is a big concern. You turn something on, and those transients can cause a big problem. They can cause actually a huge problem if you're not careful. So what happens? Well, we don't just launch off into a sinusoidal signal that we're all familiar with, comes out of the wall. We wind up with some initial transients before we get to the sinusoidal signal, and we need to be careful of those transients. And so what does our solution form look like again? Well, dc of t, a1 e to the minus t over 0.01, or if you prefer, minus 100t. That homogeneous term is always there. So it doesn't matter what the source is, again, it's always there. And what do we have now? Well, now things get a little bit more complex, perhaps. Cosine 50t plus a3 sine 50t. So this takes the same form as our source, but remember an exponent or a sinusoid has both an amplitude and a phase term. And I tend to write them like this. You can combine this into a single sinusoid with an amplitude and a phase using trigonometry that I can never remember. But this is my preferred representation. It's still a single sinusoid, and it works. So how do we find A2 and A3? Again, particular solution, we need to go to the differential equation. So nothing's changed. That exponential was fairly well behaved. This guy may be okay, I don't know. So we do the same thing we did just a moment ago, but we have two coefficients defined, or if you are a big fan of single sinusoid, a coefficient and a phase. Either way, it comes out to be the same amount of math. So RC 0.01 d by dt, and we'll set this up, but we don't have to finish it. There's our differential term plus A2 cosine 50t sine 50t equals 5 cosine 50t. And again, this is the t greater than 0 differential equation. This is why we have our source term. How do we solve this? Well, you match up cosines and you match up sines. So you wind up with two, I guess, independent terms. So minus 0.5 A2 cosine 50t plus 0.5 A3 where am I? Sine, sorry. Cosine 50t plus A2 cosine 50t plus A3 sine 50t equals 5 cosine 50t. Two equations and two unknowns essentially is what we have here. We match up our cosine terms and match up our sine terms. So minus 0.5 A2 plus A3 times sine 50t equals 0. That guy doesn't matter then. And then likewise, 0.5 A3 plus A2 minus 5 cosine 50t equals 0. And again, that guy doesn't matter. You have two equations and two unknowns. Solve for the coefficients that give you zeros. Looks like a good test problem. Not too much math. A little bit beyond the scope of what we look at, but a good thing to see. So that was to find the coefficients of the particular solution. How do we get the A1 that I just put away? How do we find this guy? Well, we go back to our initial conditions. Our initial conditions are still 0. Once we know A2 and A3, we plug in VC0 minus equals VC0 plus equals 0. Solve for A1. One equation, one unknown. So that's the tool we need to use for more complicated sources. Everybody okay with that? A good thought problem. Something to be aware of. We will see it. And I'll show you where it gets a little bit more problematic when we look at second order circuits, why it can cause failures. Now, for completion's sake, we do look at the RC circuit a lot. I tend to do that more as an example, but there's an RL circuit as well. So the RL first order circuit, and I like to save this circuit for a test, so I don't do it as much. So we have a source, we have a resistor, and we have a current. So there's our first order RL circuit. And again, we can ask all the same questions we had asked before. You know, we can say IL, IR, VL. You know, what are these parameters? VL, of course, being VR, since they're in parallel. How do we find these things? Well, we go back to circuit analysis. So IL, what's our differential equation? Well, what's a good choice? Use KCL. That's a good choice, so we can do KCL right here. And we wind up with, we call that IR, using our normal conventions, plus minus in that direction. IR plus IL equals I source. Right? No problem there. Since I drew our I source going up, but again, it's a transient situation, so it could be up or down. Well, here's our parameter of interest. And this is controlled by user, which means known. You know, it's something that we can use, turn on using a function generator or something like that. And this guy we want to get rid of. Need IR in terms of IL. So what relationship holds? Well, there's one always one fallback expression. IR equals what? No, not 0. V over R. So IR by Ohm's law, VR over R. But as we noticed earlier, the voltage across the resistor is the voltage across the inductor because they're in parallel. So we can write this as VL over R because they're in parallel. And we have a nice handy dandy expression for VL. which was LDIR, or LDIL dt, equals 1 over R times LDIL by dt. That's for inductors. DL equals LDIL dt. We saw that last week, and so now it comes back. We finally get to use it. And so what does that leave us? Well, that's L over R DIL by dt plus IL equals I source. And that looks amazingly familiar. So we have a different coefficient, L over R instead of RC, but it's the same circuit, right? It has to be. So our solution takes the form IL T equals IL homogeneous plus IL particular. And our homogeneous solution, when this is 0, is known. That's just some number. That's a first order differential equation. And so this is going to be A1 e to the minus, and now I have to think for a second to make sure I don't do this upside down. Minus T L over R plus IL particular, whatever that may be. And if it's a DC or a step function source, that winds up being a constant again. If it's an exponential source like we looked at, that's an exponential, it's a sinusoid, or RL time constant is tau equals L over R. So those are our two time constants with regard to first order circuits. It's worth making a note of. And the process is the same. We find the DC steady state. If we're looking at step functions, we can find then the constant term. So again, if I source equals some I naught U of t, some source that turns on at t equals 0, well, IL of t equals A1 e to the minus t L over R plus A2. Constant term, we can get that from DC steady state. So step function source that turns on at t equals 0. And what is that value for our RL circuit? As t goes to infinity, what is A2 for a source that turns on at t equals 0? What's A2? For a step function source with magnitude I naught. I didn't quite hear. You know, there's a lot of mumbling there. I naught. So what happens in our DC steady state? Well, what do we do with inductors as we reach DC steady state? We short circuit them. That means we have a short circuit in parallel with the resistor. This guy's firing enough current. Where does all the current go? It goes through the inductor. It's the short. So that's the path of least resistance. That's where it goes. And there's our DC steady state term. Now, someone asked me, I think there's LiTech today, and it's come up before, what does a capacitor, or what does an inductor do? Well, we know a capacitor stores charge. In a weak sense, an inductor stores current. It's kind of a very loose definition, but an inductor kind of stores current. So you can't, one thing you can't do, just to think about things a little bit physically for a moment, introduce a new component part. If this is a voltage source, and we have a resistor, and we have a switch. Can you open and close that switch at any time? So in PSpice, it's usually used as U. This is a switch. Can you open and close that switch at any time? Anyone want to hazard a guess? Yeah, sure. What's the rule on capacitors? No instantaneous change in voltage. You could charge it up, pop open that switch, no problem. There might be a little bit of sparks going on, but that's a mechanical thing. We'll blame the mechanical engineers. So you can open and close the switch at any time in an RC circuit. Well, what if I do the same thing for an RL circuit? Can you open/close this switch? Can you do that? No. So at DC steady state, if you think about the switch being closed, we're at DC steady state, the current going through the inductor is I0, whatever that is. If you open the switch, what happens to this circuit? How much current goes through an open circuit? Zero. So all of a sudden you violated the rule IL 0 plus not equal to IL 0 minus. You can't do that. And actually that's a real thing. I mean, if you've seen big power systems, they're historically, things are a little different now, but historically there were big knife edge switches. So how do you shut off power when current's going through an inductor? And actually where is a very common inductor in the power system? Transformers. So transformers are essentially inductors that are coupled together. So they're pulling current through them. How do you open the power system, especially if things are going catastrophic and you really need to shut off power? You need a pneumatic press. So you need a very strong mechanical system to force open power, to force open the switch, because the magnetic field or the current here actually keeps trying to pull that switch closed, and it's a lot of energy. So you can't do this. Now, sure, you can do it in our circuits, you're not going to have any problem, but you probably, I mean, you'll never notice it, but if you try to do it with a capacitor, no problem, you can pull the wire out. If you try to do it with an inductor, it's a micronewton harder. Our components are small, so you can't notice it, but in a big power system, it's a big problem, so you cannot, not safely, / easily. In general, in an ideal sense, I would just say no, but nothing's ideal, of course. So this is not safe. You can't open this switch. If I move the switch here, is that okay now? Yeah, sure. So you can't disconnect the inductor. If I move the switch there, then the inductor can discharge through the current. The discharge again, or lose current, discurrent if you want to. So that's okay. So as long as the current has a path, you're okay. Well, RC circuits are fun and all, but life is always a little bit more complicated than that. A simple RC circuit is Is this a first order RC circuit? First order meaning the differential equation, of course. Is it first order? You want to vote? Yes? Who says yes? Who says no? Who's checking their phone? So abstaining. One component, only one capacitor. First order. Doesn't matter how many resistors you have. Only one capacitor, first order. Likewise, you put in parentheses, only one inductor. Also first order. So, only one capacitor and no inductors. Maybe we should add that little qualification as well. And no inductors. And here, and no capacitors. So you only have one capacitor one capacitor or only one inductor. Still first order. Well, how would we find VC of t? So we need a differential equation. Still going to be first order, of course, for VC of t. Well, how are we going to get that? Where do we always go back to? Circuit analysis. So we go back to the unit 1 material, and we do either a KCL or a KVL. I favor KCL. Let's look at A there. So KCL at A. Well, what do we wind up with? VA minus V source over R1 plus VA, and we can throw a little grand on there just for completeness. VA over R2 plus VA minus VC. And these are, again, are all functions of time. I'm not drawing the parentheses of time in there. And so there's a nice KCL expression. Here's our parameter of interest, VC. There's our forcing term, or our source term. So we can do a little bit of rearranging here. We can rewrite this as VA times 1 over R1 plus 1 over R2 plus 1 over R3. Minus VC over R3 equals V source over R1. So we have our source term on the right side, where I personally like to put it. Your others may vary. We have our parameter of interest, and we have a VA. And we don't want VA. So we need VA in terms of VC, right? Just the same process we did before. There's our VA. Well, arguably we could apply a series circuit. We recognize VA for our given source is VR3 plus VC, right? Everyone agree with that? The voltage at this node is this voltage plus that voltage. It's a voltage divider in a sense, and it is a voltage divider, part of that voltage being across the capacitor, part of it being across that resistor R3. Well, I mean, we partly have VA in terms of VC. We just need to get through that, get rid of that VR3. And again, Ohm's law is our friend. So IR3 times R3 plus VC. And we know what IR3 is. IR3 is IC. Because there's only one path, right? The current going through R3 better be the same as the current going through that capacitor. There's only one path. Because IR3 equals IC. They're in series. And we know what IC is in terms of capacitors. So lo and behold, dVC by dt plus VC. Yay! So we can substitute that in up above. We can go and celebrate. So this winds up being 1 over R1 plus 1 over R2. Oh, and I left off of R3 in there. Sorry. Plus 1 over R3 times R3C, dVc by dt. And then we can substitute in our other term, plus 1 over R1 plus 1 over R2 dc equals v source over R1. Then we can do some mathematical rearranging, clean things up perhaps. But that's it. We now have the same form. These are all numbers, 1 over R1, 1 over R2, 1 over R3, times R3 times C. And we can find these values. And probably should bring the R1 out to this side, squeeze that in there, squeeze that there, as the case may be. Just because I like my source by itself. That's just a little bit of algebra. Good times. Well, R1, R2, R3, R4, R5, C, V source. Can I do that again in this circuit? Absolutely. I could do some substitution. It would take me, if I was careful, maybe 7 or 8 pages of blank paper. If I was lucky, I'd get it right without making a stupid mistake like I probably do. Well, if we think about this though, so here's this expression for the previous problem, and I just boxed it for no reason. It's not something that's worth boxing. Just a flag. If we look at this from our end of Unit 1 concept, if I cover that up and told you it was an R load, what could you do? You could do Thevenin and get a simple V Thevenin, R Thevenin, R load circuit, right? When we were talking about R load, I said it can be a whole mess of stuff. It doesn't matter what that load is. In this case, that load is a capacitor. And so, this is just some arbitrary load. We can put a box around it. It is some black box load. What does that mean then? We can do V Thevenin to get our RC circuit. Why do we want to do that? That RC circuit was easy. We've solved it 15 times already, and we can write the solution down. So what do we want to do? There's R1. There's R2. There's R3. There's the open circuit equals V Thevenin equals what? Well, I hope you agree. This is fast, but R1 plus R2 times V source, right? That's V Thevenin. This guy doesn't matter. This winds up just being a voltage divider. We've done this problem a number of times before. And we can look at the R Thevenin circuit. And again, I tend to label my nodes for no reason. We're looking at R Thevenin looking in, and that's R3 plus R1 is parallel with R2, which again is some number. And now we're done. That's great, because we can go and say our circuit, our circuit now looks like this. RTH, which is R3 plus R1 in parallel with R2. And that will be some number. And then V Thevenin equals R2 over R1 plus R2 times V source. Anyway, times C, of course. And that's great. So we can use one of our Unit 1 tools to make our life easier. Isn't that good? That's good news. So no matter what type of first order circuit we look at, whether it's something like this or even something more complicated, we can still use our Thevenin analysis to get this simple RC circuit. And in this particular case, once again, we can say B, C, and T, some A1 e to the minus T over R Thevenin times C plus BC particular, whatever that particular. And again, if we're looking at step functions, that's of course going to be a constant. So once we have it in this form, it's a solved problem. Equivalently for inductors, what do we look at? Someone just said it. I Norton. You want the Norton circuit. So if we have a big mess of resistors and a single inductor, we can reduce it to this using short circuit or Norton analysis, whatever term you prefer. And again, our solution would be IL A1 e to the minus T over R L over R7 plus IL particular. So that's the beauty of first order circuits. Unfortunately, this doesn't work very well with second order circuits. So, Thevenin is useful, and you will see it again probably in another class. Thevenin is very, very handy. Are we still writing?
Yeah.
So the V Thevenin circuit and the I Norton circuit, a useful goal. Because it's a solved problem. I mean, we love solved problems. Do you really want to derive this differential expression again? I don't. And since I'm not teaching this class next semester, I don't have to. Yes, some of you may see me again in a different class.
What are you teaching next semester?
It looks like I'm teaching electronics. So maybe good news, bad news, I don't know. See how it plays out. So as you plan your schedule, something that you can happen. I may teach fields away. No, no? A lot of crying out there right now. All right, so that's a nice, useful application of circuit reduction to our Thevenin equivalence. What we've done all along, what we've done so far in source is to turn on at t equals 0, but that's not necessarily the case. Remember we said VC 0 plus equals VC 0 minus, and IL 0 plus equals IL 0 minus. These are continuity conditions. For both voltage across the capacitor and current to an inductor, of course. So, well, this can be general. In general, we don't have to say 0. That's always true. So, a term we'll use T0 plus equals, that's a C, T0 minus. And IL, T0 plus equals IL, T0 minus. The same continuity conditions. So that applies. What this says is it applies for all time. And we already know that. but we've been using 0 plus and 0 minus for so long that it's worth noting this applies always. And so, as we think of step functions, again, essentially we can say a step function with a delay. So, of t naught seconds. How do we write that? Well, u of t minus t naught. So that's a step function that turns on at t naught. So if we plug in for the arguments there, the rule of a step function, argument less than 0, it's 0. Argument greater than 0, it's 1. And so our step function now turns on at some t naught. So it's a delay. It doesn't turn on until 5 seconds after 0. What does that mean for us in our representation of circuits? Well, in this particular circuit, again, if we look in an RC circuit, so if our V source is some 10 u of t minus t naught, so a source that turns on at some arbitrary time t naught after 0. Well, what does our solution look like? We're still going to have that same homogeneous term, and we're still going to have a DC steady state term, right? Our solution is going to look exactly the same, but shifted. So solution is the same. As t equals 0 case, but shifted, or if you prefer, delayed. So if you think about it, this delay doesn't really do anything other than change our 0 reference. Well, we could redefine time. Why not? In this simple problem, we could redefine t naught as 0 seconds, right? Doesn't do anything. That's a linear shift in our coordinate system. No problem. So what does that mean for our solution then? Well, BC of t, still an A1, either minus, let's put the parentheses over there, up there, RC, plus an A2. We still have a DC steady state term. We still have our homogeneous decaying exponential. T minus T naught. There's our shift. For an arbitrary start time, this function starts at T naught. So this solution would be valid for T greater than T naught. So to be a little bit more mathematically rigorous, we would write something like VC of T equals 0, T less than T naught, and I didn't solve for these coefficients, but we could, of course. T naught less than T. And we can see our limiting case. Once again, if T naught is 0, it goes back to our very familiar form, an exponentially converging value. And so this is the general form for a source that turns on at some arbitrary time. In our analysis, what I usually say is put this in at the end. Treat the circuit as if it's turning on at t equals 0. Do the analysis. I think that's fairly intuitive. There's mathematically rigorous ways where you can include a delay in the expression. Why bother? You know the circuit turns on at t0. Do the same analysis we've done all along. You know, this type of thing. And then add the delay at the end. Because this is only valid for t greater than t naught. So you can put the shift in at the end. So you can always do the analysis as if it was just like this, but you know it doesn't start till T0. You can add this little delay term at the end. This is an important thing to recognize as well, that this function is valid only for t greater than T0. Because if you think about it, for t less than T0, well, this term is growing. So it doesn't make sense. It's a little bit like all our exponential. In this case, for negative time, well, this starts growing exponentially. As we make this more and more before 0, this becomes a very large term. So I said it a number of times, but this solution was always valid for t greater than 0. So we solved this for t greater than 0. Now that we've shifted our time, this is valid for t greater than T0. So how does that come into play? Well, let's consider V source is a pulse. Let's give ourselves values 1K and 1 minus 6. So, if V source is a pulse, it looks something like this. Some period of time it's on, that's 0 to some t, and then it turns off. As we consider this problem, well, the very first thing we would do is start to be a little bit more mathematically rigorous. dc of t, as we have some solutions, well, again, we can look at t less than 0. This is a 0 initial condition problem. There was no source term for t less than 0, but to fully specify it, we could say this is 0 for t less than 0. Right? And before I start putting in numbers, well, we also have some period of time, and I'll just call it dc1 of t, for 0 less than t, less than capital T, right? We can find some solution while the pulse is on, while the pulse is high. And that's its own particular solution. And now we have another solution for t less than t. Why do I divide it up like this? Because each of those, I call them regions, corresponds to a different circuit. I mean, essentially, we have a pulse, but what does that mean? It's a different circuit. And we can quickly draw these circuits. So our t less than 0 circuit, well, that's just shorted out. So that's our 0 initial condition circuit, no source. Our 0 less than t, less than capital T circuit, well, our source is on. It's some constant value, some d naught. If we're working with step functions, of course. And then our t, capital T less than t circuit. Once again, we turn the source off. And granted, these two circuits are the same, but they happen at different instances in time. So the first and third circuit, yeah, they're equivalent circuits, but they have different conditions. This is a 0 initial condition situation. could be V naught. Under what situation would it be V naught? Yeah. Fully charged, but more specifically, if we waited a long time, right? We kind of discussed long time in the last class. A long time corresponds to, as you just said, the capacitor being fully charged, having the full voltage. Well, we don't know that's the case until we know what capital T is. And we had that kind of loose description. We said a long time being 5 time constants. And so if T was larger than 5 time constants, yeah, that would be a long time. But if it's less, then no, it's not fully charged. And so effectively, what are the initial conditions for this circuit? Well, they're the final conditions for this circuit, right? Initial conditions are from final conditions of previous circuit, or above circuit, previous. In other words, we call this VC1 of T and VC2 of T in our previous page, where we define the solutions, just general form. So what does that mean for us? Well, VC1 of T minus equals VC2 of T plus. Right? So our different expressions still have to have continuity. You have to have continuity of the terms. And that's a big deal. So, well, in general, for this problem, let me go ahead. And I picked those numbers because they represent tau over 6. Tau equals 1 millisecond, 1K times 10 to the 6. And so this is tau over 6, and this is tau over 6. Right? This is 10 to the 3 times 10 to the minus 6, 10 to the minus 3, which is 1 millisecond. So, we can do some analysis here. Usually when I start these problems, and this is the way back when I first started teaching, I would say define the regions. So I call it solution regions. And we already have done that effectively. The source defines the regions for us. How do we define the solution regions? We have a break every time the circuit changes. So in the team assignment we'll see in a few minutes, I have a switch in there. I also have a changing source. Every time the circuit changes, whether it's the source, whether you throw a switch and introduce a new resistor, anytime you do any of that, then you have a region. So what are our regions? Well, by definition, t less than 0, 0 less than t, less than tau over 6, rather than write out 0.166, tau over 6, less than t. What is our solution for t less than 0? We don't care. This is only gives us an initial condition, but we have 0, IC, so our circuit is 0 for that time period. Well, for between 0 and tau over 6, what is our solution form? Has it changed? We already saw the circuit. This is a solved problem. If this is a constant, this is an RC circuit. So we can go ahead and directly write A1 e to the minus t over 0.001 plus A2. It's a step function source. That means our particular solution is DC, and first order circuits always have this decaying homogeneous term. This guy goes with all our first order circuits, and again, our particular solution is a constant. Well, what is our, and that was our DC1 of t if you want. What is our solution for this region? What does it look like? What does it look like? No. And DC steady state as time goes to infinity is 0. Has it changed? Still an RC circuit. What does it look like? Same. Different coefficients. E to the minus t naught over 0.001 plus 8.4 DC2 of t. Different coefficients, same form, but now this region doesn't start until tau over 6, which is t naught. So you could put in 0.166 if you're still inclined. So here's the form. The form is exactly the same. Our coefficients are different, but the form is the same. And so how do we solve for these coefficients? Well, you start at the beginning, and we already know that. So then we go here for 0 less than t less than 0.166 milliseconds. DC1 of t equals A1 e to the minus t over 0.001 plus A2. And we do the same tools. And there's something we really want to be careful of here, which I've seen a number of students mess up. We do everything the same. When we solve for these coefficients, we treat this as if this was the circuit for all time. What does that mean for us? This is the DC steady state term as t goes to infinity. So we can cover that up. This circuit, yeah, that's the time it's valid, but when we analyze this circuit, we use this condition. Because that's going to be what's happening. If you think about it, if we left this circuit on, if we just throw the switch and turned it on, it's going to charge up. We've seen this expression a lot, right? Well, no matter when we shut the switch off, this path is the same. And eventually it reaches DC steady state. And so, no matter what happens, whether we shut it off here, here, or here, as we follow this exponentially growing curve, the form is the same. So when we find this term, this is still a DC steady state term as if t was going to infinity for this region. And that matters. And we can go back to our definition then. What is it? It's 10. There's our step function source. We turn it on, it has a voltage of 10 volts. And we can go in and say, should have drawn that at the bottom, but from our analysis, A1 e to the minus t over 0.001 plus 10. That's as t goes to infinity. First term vanishes. We know what that expression is. I didn't write that out this time, but that's 10. And we can enforce initial conditions. VC 0 minus equals VC 0 plus. We've done this already. We know we had 0 initial conditions. And so that's A1 plus 10, which implies A1 equals minus 10. And so in our solution, just to rewrite our solution out, BC of t equals 0 for t less than 0. And now minus 10 e to the minus t over 0.001 plus 10 for 0 less than t less than 0.166 milliseconds. Right? And now we need the next region, 0.166 milliseconds less than t. There's our final region. And so what is our, everybody okay so far? Everybody in trouble? I have found this to be a little bit tricky in the past. Yes? No? Not tricky? Maybe tricky? Amusing? So what is our t 0.166 milliseconds less than t expression look like? Well, again, it was the same form. We had A3 e to the minus t naught over 0.001 plus A4. That was our DC2 of t. Well, again, this is the DC steady state for this region. And that was going back to our source. Our source turns off at 0.166 milliseconds. Our source turns off. What does that mean for us? Well, what's this value then? If we let t go to infinity, 0. So that's going to be 0. So we have A3 e to the minus t naught. And I should point out that's 0.166 milliseconds. Or 0.001. Well, how do we find out what A3 is? Continuity. We said it already. VC at VC1 at 0.166 milliseconds minus equals VC2 at 0.166 milliseconds plus. So just before 1/6 of a millisecond and just after 1/6 of a millisecond, continuity must hold. Well, this is the solution that we already know. This is known, so we can plug that into our expression. We get 10 e to the minus 1/6 magically. So I took some shortcut there, but that's what it winds up being. You can verify that if you're so inclined. Minus sign, of course. Plus 10 equals A3. Do we agree? We plug in 0.166 here. That argument goes to 0, and we get A3. So here's the final value for VC1 of t. And here we have the initial value of VC2 of t. And by coincidence, in this particular case, A4 is 0. A4 could have been non-zero if we had a DC steady state term. DC steady state source, of course, we would include that. In this particular case, A4 is 0. And this is some number that I have written down somewhere. I think it's that number. And so we can go back to our solution form. what do we have? 1.53 e to the minus t minus 0.166 milliseconds over 0.001. I'm glad I didn't need more room. All right, I want to give you enough time to work on the team assignment, so I'm just going to give you a concept question here for a second, and we'll talk about it. If I have a source that's a pulse stream, turning on at t equals 0, but always off. We'll look at this problem next class, but we'll just talk about it for a moment here. What does VC of t look like? So it increases, right? And as it decays here, is it going to decay to 0? No. It decays part way and then charges up. It decays part way. And eventually it reaches kind of a steady state where the decay and the rise are equal. But we start at 0, decay, and climbs up until it does reach some sort of periodic function. And this comes back to what I said about turning on sinusoids. So we have some initial transient here. Sinusoids is more dangerous. When we look at second order circuits, we'll see that. So this is a similar type of effect. All right. Team assignment time. And it has to do with this transient. So just